welcome to this Triac phase control tutorial. On this short video we will cover the overview of a standard Triac dimmer, the hysteresis, what is it and how does it affect your circuit. Lastly, we're going to cover the circuit diagrams and the workings of the improved Triac dimmer. And we also have a present, but this is just for engineers, full of waveforms and nice diagrams in the end. Stay tuned. In here we see a standard Triac circuit dimmer. We see that when the Triac is open, there is a voltage across these two nodes. R4 and R1 will charge capacitor 1. These form a timing circuit in which capacitor 1 is charged faster or slower depending on the value of the potentiometer in here. The faster it charges, the earlier the diac is activated, which in turn discharges capacitor 1 into the gate of the Triac, which activates it until the next half cycle. Notice that R4 and C1 form an RC circuit, therefore this introduces some phase angle delay between the input voltage and the capacitor voltage. What this means is that at each polarity reversal we need to first discharge the capacitor before we can start charging it again. When the diac conducts, this problem does not occur because the diac will discharge the capacitor into the Triac gate. Therefore, we no longer can see a phase shift because the capacitor has been discharged. We can see, however, that depending on the way that the diac is being driven, there might still be some residual voltage across it. For example, if we're operating with 50% duty cycle, we can see that the capacitor is still charged to about 12 volts. However, if we operate closer to the full cycle, then we can see that the diac discharges very quickly. This means that the hysteresis is not constant and it will vary between no load, partial load or full load. Here we cover an improved circuit. We add diodes 1 to 4 along with the resistors 2 and 3 to discharge any residual voltage across the capacitor at each cycle reversal. This gives the timing capacitor a chance to start at 0 volts on every cycle and therefore maintains the timings accurate and constant. This avoids flickering or juddering of motors. During normal operation, C1 is still charged by R1 and R4. And here we can see the circuit at steady state before power is applied. C1 is discharged, no current flows. As the supply is first turned on, in the positive half cycle, the current will start to flow. R2 and D2 form a voltage regulator. D2 is forward biased, which means that in this node in here there will be a voltage of approximately 700 millivolts. The remainder of the voltage will be across R2. This serves to give it a reference point. Since capacitor 1 is discharged, there is no current flowing. As we progress into the cycle and the mains voltage continues to increase, R4 and R1 will charge capacitor 1. It will eventually trigger the diac, which will break down to the Triac. Here we see that at a steady state, when the zero crossing occurs, C1 might still be charged. On the next half cycle, the current reverses polarity. In here we see two things happening. Now there's no current flowing through R2 and D2 since D2 is reverse biased. However, D4 is forward biased, and therefore a current will flow through D4 and R3. Just as with the previous circuit, this generates a voltage of about 700 millivolts at this node, with the rest of the voltage being dissipated across R3. As long as capacitor 1 is charged to a voltage higher than 700 millivolts, the current will flow in this direction. This in effect discharges the capacitor. Once the capacitor voltage reaches 0.7 volts, no current can flow through this circuit. The current in this situation only flows through D4 and R3. The capacitor is now discharged. Notice how R4 and R1 will now start charging the capacitor. A current will flow through R4 and R1, which charges C1 with the inverse polarity to the previous cycle. Once C1 achieves enough voltage, in this case minus 30 volts, the diac will be activated and the charge will be dumped into the triac. On the next zero cross, C1 might have some residual charge on it, but C1 might have some reverse charge still stored. Again, we see that D2 is forward biased, and there will be a voltage of 700 millivolts at this node. As long as the capacitor has a voltage lower than 700 millivolts, current will flow through this node until the capacitor is charged to 700 millivolts. This effectively removes the negative charge present beforehand. At this stage, current continues to flow through R4 and R1, which will charge the timing capacitor, and the circuit works just as before. Hey, check this out! I've got some extras in here. So here in my desk I have two Triac circuits. One is the normal circuit, and the other one is our improved version we just covered with the additional two resistors and the diodes. And very conveniently in here, they thought, well, I can actually use a bridge rectifier to do this, as we're gonna see here in the diagram. So just for a second before I go into the details, let's recap how the circuit works. So the first thing we see here is that the triac will be open, so we're gonna have a voltage across these two nodes. So the capacitor will originally be at 0 volts, and then the current will flow through this resistor and the potentiometer, and we'll start charging this capacitor one. And the capacitor, once it reaches 30 volts, the dioc will break down, and it will conduct, and it will discharge the capacitor into the triac gate, and the triac will start conducting. And hopefully that's the end of the story until the next negative half cycle. Now, that's not always true, because if we have a non-linear load, such as an LED bulb, for example, and the current falls below the holding current, what's going to happen is that circuit is going to very, very quickly recharge this capacitor, and the dioc will break down and will very quickly energize the triac. But we have a situation in here where this may not happen. Let's imagine that we don't conduct, we don't reach the breakdown voltage for the dioc, and we start with an initial condition of, suppose, minus 20 volts on this capacitor. So guess what? This is a bummer now, because first thing we're going to have to do is we're going to have to discharge that capacitor all the way from minus 20 volts until 0, and only then we start our timing loop. And you know, this is not ideal, because then we don't start with the ideal starting condition. So let's turn this on and see what happens. So here my bulb is off, and we can see that the capacitor one, together with the two resistors in here, the potentiometer and the resistor, is forming an RC circuit. And if we look at the mains voltage, which is the yellow plot, and our voltage across the capacitor, we can see that basically you have an RC circuit and we have a phase shift. And this is really going to be the case all the way until the triac really, until the dioc goes into breakdown and resets it. Now look what happens in here. So we reach 30 volts, my dioc has broken down, and it discharged this capacitor into the triac. It didn't fully discharge the capacitor, so we're a little bit better, because now we only have 12 volts across the capacitor for the next cycle. But you know what, it's still not ideal, because we still have something in there. Now, as I increase the duty cycle, so as I increase my phase angle, we can see that we now approach very much an ideal situation where the dioc reaches 30 volts, and then it discharges it breaks down and it discharges C1 into the gate of the triac, and so this is our ideal condition. So now let's see what is the difference in this improved circuit, and we just covered. So I just swapped over the probes of the oscilloscope to measure the voltage across this second dioc, and now I'm going to turn on the supply voltage, and look what happens. all of a sudden you can see that we no longer have an RC circuit where we have this phase shift. Now we have this strange waveform. So here we see that the voltage reaches 0 in here, and my capacitor will start to charge from that point, which is very much the ideal condition. And then once the voltage reverses, not much happens, but when we get here to the 0 cross, suddenly the capacitor is discharged. So we have this much faster slope than we had to charge. And so when we go into our negative half cycle, we're very much at this ideal condition, which is 0 volts across the capacitor. So bingo! Now I don't have to worry about discharging the capacitor because the diodes and the resistors have done that for me. So how brilliant is this? Now, as we decrease the value of the potentiometer and we start to charge the capacitor with more current, we can see that, you know, the situation remains. We are still able to discharge the capacitor with a much higher slope than we are charging it. And when we finally reach the breakdown voltage, look what happens. So my diode starts conducting. Again, it doesn't conduct in an ideal fashion, so it only discharges the capacitor to about 12 volts. We have a rather slow slope of this capacitor discharging all the way until we reach the 0 cross. And once we reach the 0 cross, bang! My capacitor gets discharged very, very fast. And then, guess what? We are again at an ideal situation where we have a 0 volts across the capacitor, or very close to 0, and we start charging it for the negative half cycle, and the same thing happens. So we were able to remove the hysteresis on this circuit. Now if I continue to increase the phase angle, we get to a point where you know, really the Triac is working as an ideal switch and is fully discharging the capacitor across the Triac gate, and we start with an ideal condition. And here there's not really a lot of difference to the previous circuit. So this only really works if we are operating at a very reduced output where we really may miss the cycle, or we are operating at somewhere half through the cycle. It also removes this annoying popping circuit where when the Triac starts operating, it has a voltage across it, and then if you try to dim the bulb all the way to down, the bulb goes off, but then you have to put the potentiometer all the way up until the bulb gets up again, and then you discharge it again. So when you first start, you have, for example, 20% brightness rather than 2 or 3%. Which is not really ideal. So I hope this has helped you to understand how the circuit works, how it really operates in practice, and, you know, happy prototyping. I hope you can make better circuits with the Triac now. So see ya until the next video.